Welcome to Embedded. I am Alicia White, here with Christopher White. I think this week we should spend a bit of time talking about filtering, signal processing, music, and programming languages. Our guest is Leonardo Laguna Ruiz.
Hi, Leonardo. Thanks for joining us.
Hello, all embedded listeners.
Could you tell us about yourself?
Yes, so I'm Leonardo. I'm a PhD in electrical engineering, and I kind of live a double life. During the day, I work as a software engineer in Wolfram research, but during the night, I work on my own projects, which is, I have a small company called Vult, where I do mainly things related to sound synthesis.
What does Vult mean?
Vult, I got it. I got the idea as like from some crazy dream where I had visions of vultures, and when I started developing these things and I needed to set a name, I said, Vult sounds good for vulture.
Okay.
And it has been there for a while. So.
Well, I think we're going to do lightning round now, and you're a listener, so you know how this goes.
Yeah, and I'm nervous.
All right, ready?
Ready.
Favorite chord?
F sharp.
CV or MIDI?
CV, definitely.
What is CV?
Okay, control voltage, yeah.
Favorite instrument of all time?
I think it will be definitely the guitar. Especially the Les Paul model. I really like that model.
Favorite fictional robot?
And this is a difficult question. I will say that my favorite is Ava from the movie Ex Machina, because it is like the only cute robot that shows the real intentions, which is to deceive and manipulate humankind.
Software or hardware?
I cannot pick one. I think I will say both.
Complete one project or start a dozen?
I used to be the kind of person that started a dozen, but in recent years I have moved to starting only half a dozen and finishing one.
What is the worst 80s synth song?
I don't know. Since I was born in the 80s,
Okay.
and I'm pretty sure that there are lots of songs that are really bad that I never heard. So I only know the good ones.
Very good, very good.
Okay, let's get on to the longer questions, because some of these require a whiteboard, and so we're going to have to talk around them. You said that the vultures told you to make filters. No, wait, that wasn't quite what you said, but something like that.
Yeah, something like that.
What do you actually do in your spare time or in your non-work time?
I like to do a lot of sound synthesis projects, and the filter part, it came a little bit late. So before I was just trying to program like small microcontrollers to do wave generations, etc. But then one thing that I have seen while doing these projects is that the filters are almost never done digitally, because from what I read, they always say, do your sound generators digital, but do your filters analog. And I was wondering why. So why the filters are done always analog? And then I fall into this rabbit hole of filters, and I started making a lot of analog filters and modeling filters, and that's how I ended up in recent years making mainly filters, digital filters.
Christopher's brother Matthew plays guitar and has a large number of amps and says things like, these tubes are the best. and I can only get them from Russia, and they're marked radioactive or something.
You're just making stuff up.
I am totally making stuff up. But he is very focused on
Yes, and
the
he
tube
likes
sound.
analog stuff. Yeah.
Does it really sound different? Is this like having gold Ethernet cables?
Not quite, but let him answer.
I mean, probably, there is part of is related to the gold Internet cables, because there is one thing that analog components have. They are imperfect, and they tend to sound more pleasant than the digital counterparts. So if I make a guitar amp that uses the lowest distortion, the best operational amplifier or integrated circuit, and I plug my guitar, it's going to sound really nice. I mean, but it will not have that charm. So it's a bit like eating boiled potatoes and eating French fries. The boiled potatoes are, they are good. You can, they're practically the same thing, but for some reason the French fries taste much better. And this, well, and in the case of the specific case of the tube amplifiers, the fact that these amplifiers introduce small imperfections to the sound makes this sound specifically for the guitars more interesting.
So amplifiers amplify things based on the name, and filters filter things, which seem kind of like the opposite things to do. Why do we talk about them together?
So, filters are they remove frequencies, so we can think about them as amplifiers for frequency, right?
Yeah, that makes sense.
And in the case of synthesizers, filters are used in one specific kind of synthesis, which is called subtractive synthesis, in which you start with waveforms that have a high, that are rich and high, have a high content of harmonics, but then you can put filters on them to remove some of those harmonics, or to shape them just to get the kind of sound that you want. For example, I'm thinking in a very basic synth sound. Let's say that I want to make a sound of a piano, and it is basically what I need is to model first the impact of the sound when I press the key and the string is hit.
That's like the attack, right?
Yes, the attack. And for that, I need more harmonics to have like this initial explosive sound.
Because it's actually a high frequency sound. It's got all of the frequencies.
Yes. And as the string resonates, the higher frequency harmonics are being consumed, and then you get only like the fundamental oscillation of your string, and that is very close to a sine wave. So if I would want to imitate that, it will be possible to use like first an oscillator that produces more harmonics. Then I use an envelope to just like open the filter during a small period of time, and then closing the filter gradually in order to get like that sound of the release sound of the piano.
So one of the things about synthesizers is it's not just you have a filter and you set it to, okay, here's this notch I'm going to remove, or here's this set of low frequencies I'm going to remove. You actually manipulate the filter in real time as the sound evolves.
To like change the envelope over time, even so that if you press the same note 5 times, it sounds different.
Even within the same note hit, it might open up.
Okay.
Or close.
Yeah, that's exactly one big difference between the kind of filters that we study, for example, in electrical engineering. When you design a filter, or when you read a text on designing a filter, you pick a frequency, you select your components, and you implement your filter. But in the musical filters need to be controllable, and they also need to be controllable in an exponential way. That way, it matches the way the notes change. For example, a C note in a piano. You have many C notes in a piano, and the difference between those is that each note has the double of it doubles the frequency, right? Each octave,
right,
doubles the frequency. And in the case of the musical filters, you want to control them in the same way. So you don't say, right now I'm in 100 hertz, and then I'm in 110. The relation between the controlling voltage and the frequency is this exponential. So it sounds nicely with the in a musical scale.
And you can go pretty far with that too, to the point where you're only playing the filter. Like on one of my synths, I can set the filter to get into a kind of self-resonance.
Yes.
And then control it with the keyboard. And so it's the only thing that's actually, it's getting some noise from inside whatever's left of the synthesizer, and that's resonating in the filter. But the filter's tuned with the keyboard, so you're actually basically just playing the filter.
So in an electrical engineering term, this is like terrible.
Yes.
I mean, this is the opposite
yes.
of what you want. But because you're doing music, and music is often not intuitively mathematical, graspable, you go ahead and you use these effects. And that's also like why people like tubes, is because they're imperfect.
Yes. I was thinking, for example, the other day I needed to read a temperature using an analog voltage, and I wanted to convert it to use a simple amplifier just to get a wider range. I mean, a larger signal value. And the thing is that this sensor that sends, I don't remember exactly, but let's say that it sends me 10 millivolts per degree, per Celsius degree.
Mm-hmm.
I wanted to convert it to 2 volts. So I need to amplify it a lot. And so I make an analog amplifier for it. The problem is that this analog amplifier can only output voltage that is between the with a margin like less than the positive power supply and higher than the negative power supply, right? So the two rails. It cannot. If I feed the amplifier with 12 volts, I cannot get 40 volts out of it.
Not for very long, no.
Yeah, probably not for very long. And the thing is that filter will be like that amplifier will be very bad because I have very short range. But if I plug my guitar on it and I use exactly that amplifier, I'm gonna sound like Jimi Hendrix. So from the engineering point of view, it's a bad design. But a musician definitely can do something interesting with it.
Why? Why are our brains? Why is it that our brains are wired to like the imperfections, or is it that we are culturally wired to prefer these things?
Yeah, I don't know the answer.
Yeah, there is one thing that the distortion makes, and is very is easy to measure. When there is a little bit of distortion, we're introducing like high frequency harmonics. For example, if we have a pure sine wave and we see the spectrum, you will only see like one bar, right? Mm-hmm. 1 point. But when you add a little bit of distortion into this waveform, you will see that that in your frequency analyzer, they appear like small frequencies, higher frequencies. and the more you distort it, you get more of this, and it just makes it sound more appealing.
So if you're going to make a model of an analog synth or an analog circuit as part of a synthesizer, you're actually going to do this in digital. How do you just play one of the original and capture its spectrum and envelope and then recreate it? Is this how you go about modeling it, or is there a different way?
No, a little bit different, because if I'm gonna tell you a little bit about the process. So what I usually do is I take one of the existing filters. Like there are lots of schematics online that you can find, and let's say that I pick one of those, and then I start analyzing what's the basic architecture of the filter. So if we take one, let's say a Sallen-Key filter, which is also quite common.
Sallen-Key. Okay, it's a high-pass, low-pass filter?
Yes. And many of these musical filters have a variation of this one. But in order to change the cutoff frequency in this architecture, in the Sallen-Key, you need to change two resistors. And many of the synthesizers, since you don't want to put variable resistors there, you want to control them with voltage. There are different ways of doing that. For example, with diodes and changing the biasing of the diodes, you can put transistors, FETs, etc., in order to simulate, not to simulate, to have this variable resistor. So what I start doing is using like this program that I write, this simulator that I write in Wolfram. I start making a component model of this circuit. You can think about it as just making a SPICE simulation, where you put all the components, right?
Okay.
The main problem with the SPICE simulator is that the models maybe are too complex. If I put like an operational amplifier model, it will contain minimum 12 transistors. I'm simulating like these 12 transistors. But with the simulator that I use, I can replace that complex model by a simpler one. For example, in the case of the operational amplifier, the simplest model will be just measuring the voltage between the inputs and adding a gain. And then I can consider other effects. And this is where it starts getting interesting. So let's say that I make my model. I use resistors, capacitors, and an operational amplifier. If I make this model of the operational amplifier linear, I will get a linear filter. And the linear filters, sound okay. But if I want to simulate the analog feeling of this, what I need to do is to make a model of the operational amplifier that behaves just like my real amplifier, which will be it has clipping. It is exactly what I mentioned before. The amplifier cannot output more voltage than its rails. Then I have to add like this limiter. And once I put this non-linear operational amplifier, my filter is going to be non-linear, and then and from this circuit, just by following the basic electric analysis methodology, like nodes, like getting all the currents of the nodes, I can get a set of equations that I can start simplifying more and more until I get like the smallest representation that will be a set of non-linear differential equations. and that this will be the small representation of my model. And these are the equations that I need to simulate in order to imitate this specific filter.
So it's really a component level model that you start with, not a behavioral.
Well, it depends. It's a mix. It's a mix of it. Yes. So I usually start with the component level, because at the component level is the one that allows me to analyze which things are the ones that I have to model. So let's say that my filter has 4 operational amplifiers. Maybe not all the 4 need to be nonlinear. And in order to determine that, I usually just do a comparison with the real circuit, which I either made it in a PCB or have it in a breadboard. And then I input a signal and I check. Okay, so if I put my filter into this configuration, what's happening? Okay, this operational amplifier is saturating. This one it always works in the linear region. Then I can replace it for a simpler model. And that's part of the analysis. Trying to figure out what are the things that matter and what doesn't matter in order to get a simpler model.
Are there any popular filters that have just not fallen to this technique, that are just too complicated?
I'm not sure. I think that at least I have been able of simulating like reasonably well most of them. But what the problems that I have had is that since I want to model this filter and then simulate it in a microcontroller, I don't have enough CPU to do that, and then I have to drop details of my models in order to be able to simulate it. So my model will not sound exactly the same, but it will sound pretty close, and it will be much more efficient. To give you a specific example, I was modeling a filter found in a Russian synthesizer called the Polyvox, and they use these special operational amplifiers in which you can send a voltage, and that controls the bandwidth of the amplifier. And in order to model that, so first I had to get the operational amplifiers, then making the model, and the model that I got, it was too complicated. The differential equations were very hard to solve, and then I had to simplify a bit my model in order to get something that sounds close, but it doesn't sound exactly as the original.
Have you trained yourself to hear the differences, and does that affect your enjoyment of music?
Yeah, like the worst thing about working with something like this is that you cannot listen to music while working, because I need to be listening to a continuous waves sound for a long time, for long periods, and also the ears get tired. So I also use a lot the frequency spectrum just to find out, to help me visualize what I'm hearing. Yeah, that's bad. And also, my wife gets very upset because I'm playing a sound like 2 hours.
We're sponsored this week by QT, or Qt. I'm super excited to have Qt as a sponsor, as I've been a fan for years. I've built entire medical devices using Qt, as well as tons of small utilities for things like firmware update and microcontroller config. Qt is a cross-platform application framework based on C++. That means you get a full set of libraries for nearly everything you can think of, plus a world-class GUI that will give you a native look wherever your code runs. You can target 16 different desktop, mobile, embedded operating systems. Write your code once and run it nearly everywhere with minimal modifications in one SDK in one language you probably already know. It's awesome to take something that started on Windows, move it to Linux, macOS, even iOS in a matter of days, and have everything scale and appear native for the new target. Qt's fast design and development workflow is trusted by over 1 million users worldwide in over 70 industries, including automotive, medical, automation, and aerospace. Version 6 has just been released and has a bunch of cool new features, including C++ 17 and Python support. It has a new graphics architecture that supports the latest GPU APIs. Developing adaptive, scalable user interfaces in Qt has gotten even easier. They're also announcing a brand new product that I'm super excited about, Qt for MCUs. I wish I had this 2 or 3 years ago. It is a tiny footprint version of the full-fledged framework. You've got the same rapid development tools in GUI Designer now for a smartphone quality user interface on your embedded project. Since the tools are the same, you can prototype and test your UI without hardware right on your desktop. Qt for MCUs targets RTEST-based systems or bare metal on a variety of MCU families. I'm thrilled about this and can't wait to try it. If you'd like to try Qt or Qt for MCU yourself, go to qt.io/embeddedfm and sign up for a free trial. It includes all the frameworks and development tools, along with a bunch of cool demos of desktop, mobile, and MCU applications. Qt made my development life so much easier dozens of times, and I think it can do the same for you. Thanks again to Qt for sponsoring this week's show. I wanted to ask, just briefly before we move on, about you said you get it down to a minimal set of nonlinear differential equations. And those are not easy. There's various techniques for solving nonlinear differential equations, but they aren't as approachable as linear differential equations. What methods do you use to solve them, and how do you fit that into a micro?
Yes. So I use it depending on the filter. I have one of the advantages that I think I have is that in my real work I develop a simulator. And over the years, I have accumulated a lot of knowledge on how to simulate differential equations. And in order to fit them in the microcontroller, I use a lot of things. For example, one of the part of my analysis, once I have the differential equations, is to find a method that is suitable for this set. Because if I want to simulate an RC filter made with one resistor and one capacitor, probably the Euler differential equation, the Euler method for solving differential equations will be enough. So I don't need to have to do more. And if not, for other filters, what I do is try all methods that I know: Hune method, Runge-Kutta, trapezoidal integration, and then I try to find which one fits better into this. To solve the equations and to have more or less accurate results. And then then there comes another problem, which is performing the computations. And since I have nonlinear elements and I have to do iterations, I have a bag of trickery to write the code. For example, using a lot of lookup tables in my code to try to speed up the computations. If I have a long formula that I need to evaluate and it's only one variable, it works making a lookup table for it. So from all the equations I try to do that, and also I try to use mathematical simplification as much as possible in order to reduce the number of multiplications, which are usually the ones that tend to be more expensive.
It sounds like it's mostly time domain, though. When I was doing this stuff years ago, one of the techniques was to do a Fourier transform of the nonlinear DE, and then do Runge-Kutta in frequency space, and then move back or something like that. But this sounds like all time domain.
Yeah, I usually do the time domain because once I have this set, if I apply this technique, and I make it efficient enough, it will work fine without doing back and forth Fourier analysis.
That's cool.
Well, one of the problems with doing the Fourier analysis is you need a window to act upon. And as soon as you have a window to act upon, now you're delaying your signal.
Yes.
And that has all kinds of problems associated with music.
Yes. So one of the big problems in the filters is that you usually have feedback paths in your in the circuit. So if I split, let's think about one of the popular filters, the Mooc ladder filter, which is basically 4 low pass stages, and then you have feedback. If you model this one as 4 separate low pass stages, and then you take the output sample and you feed it back to the input, you get a filter that sounds different because you have a delay in the output. And in order to avoid that, I need to analyze the system, including the feedbacks, and that's usually why I need to solve the differential equations, because I need to iterate. I need to have the iterative method in order to solve this feedback path.
You've implemented a pretty long list of filters, but I don't know what they sound like. Are there ones that I would recognize based on certain songs, or are there ones that are special beyond those we've talked about?
I don't know if not you, but a person that is not into the synthesizers will recognize them.
I can't even tell. I mean, I've got several, and I kind of know what these things do. I couldn't tell you which filter was which in a song.
Okay, then tell me about this one. Debriatus, a wave destructor with bit crusher, wavefold, and distortion?
Yes. Yeah, that's not a filter, definitely.
What is it?
That's another. So in this module for Eurorack that I make, I included a lot of filters. So most of my filter models are implemented into this module, and it's possible to switch between them just by the press of a button. And since I have a module that can do that, and I have a processor, so I decided to put some of my other virtual modules into this one, into this real module, and that is basically a distortion, because you can always take your audio signal, spice it up a bit with bit crushing, saturation, distortion, and then put a filter after it to get it back to nice levels.
A bit crusher that's where you take the bit depth of a digital signal and chop it off, right? So if you have a 16-bit digital signal, you truncate it to 8, and it sounds grungy and gross, yes. And then you fix it up with a filter.
Yeah.
You mentioned Eurorack and modular synthesizers. Could you explain what that is for people who aren't surrounded by a lot of synthesizers?
I have no Eurorack in this house.
Yes. Okay.
Is that what you want for Christmas? Sorry, go ahead.
Okay. So basically, or the common synthesizers that people may have seen, they consist of a bunch of buttons in a keyboard form factor.
Yes, I see that.
And those are the like fixed synthesizers. Let's call them that. So integrated synthesizers, in which the architecture of your sound, of your synthesizer, is a little bit fixed. It follows a traditional path in which you have sound sources, filters, and then you have modifiers, and you can do a lot with those synthesizers. But there is this other kind of synthesizers which are the modular, and one of the most common form factors is this one, the Eurorack. And the main difference is that instead of when you want to build a synthesizer, instead of buying one that has everything, you buy individual modules. So you can say, I want an oscillator, and I like this one from this manufacturer because it makes this and that. So you buy that one, and you have an oscillator. And your panel, the panel of your module, has jacks, audio jacks. And then you can just take that audio signal and insert it into any other module that you want. So you can say, I want a filter. And you buy like a 1, 2, or like me, you end up having 32 filters, 32 analog filters. So you pick one of those, and then you can send your signals. And so the main difference is that you have like full freedom to construct your synthesis machine and to rewire it with physical cables.
Like, if you were to play this live, would you be rewiring it live, or is it you wire it and then that's how it sounds for however long this song takes?
It depends on the artist. I have seen a lot of videos of people that actually play live with modular synthesizers, and they usually have it a little bit fixed, because when you have a synthesizer that is that big with so many cables, it may be hard to rewire live. But you can always do a little bit of patching. So probably changing a few of the jacks that you remember, because I have a small Eurorack synthesizer, and I have probably 60 patch cables. And when I'm designing some sound, sometimes I use them all, and I'm not doing anything complicated like a live performance. So I cannot imagine a live musician patching 60 cables in a single session.
Most of the time, they're probably twiddling the knobs and things that affect individual modules and not rerouting things.
Yes, and there are even modules that help you do that. If you don't want to change cables live, you can add a module with switches. Then you can just toggle switches to change your routes.
Usually what happens to me, even when I'm using a non-modular synthesizer, is I'll start playing with it and then not make any music because I'll be so busy changing routing and getting so into that part of it. Like, oh, I'm designing this sound. Oh, what if I connect this to what if I turn this knob? And then 3 hours have gone by and I haven't actually, I mean, it's fun.
Yes, that I agree. That's what I usually do. I never, so I just get lost into the sound design. So bad that I haven't made any song in 4 years or something, 3 or 4 years. Just sounds.
But you have been making this unit that can go into the Eurorack that then can model, simulate, mimic a whole bunch of other different modules that would normally go in the Eurorack.
Yes. So that's. I mean, before we have been talking a lot about filters, and I do all this. I do all these models because I want to put them into this module, which has an ARM microcontroller. And the idea behind that, it was to have this digital module that, just like the robots that I mentioned before, it tries to deceive you and manipulate you to think that it is an analog filter, but it is not. It's digital, but has the advantages that you don't have. To use a lot of space with a lot of filters, and maybe if you're just picky like me, you want a specific sound, and then you can easily just change which filter you want for this specific sound.
Well, then you don't need to change the patch cables. You can just change which filter you want.
Yeah, I mean, you can change the filter, but you can still change a lot of things in your sound system, in your sound generator.
There's a completely simulated Eurorack called VCV Rack. Is that right?
Yes.
Okay.
Yes. So VCV Rack is this open source Eurorack simulator, which it was developed by a person called Andrew Vult. And since it is open source, it is very easy to create your own modules. And it simulates the Eurorack because it follows the same form factor. You have also like traditional Eurorack panels, and then you can plug, do all the patching with wires. And it simulates it. Well, it tries to simulate all except the bad things. For example, you cannot connect outputs to outputs, or doesn't let you inputs to inputs. And yeah, it is really nice. So I actually started developing all this for VCV Rack. Since I've been developing models for a long time, when I found that VCV Rack was going to be launched, I did my first module was this virtual filter for VCV Rack, and I got excited and I kept doing more and more and more. And what I did, it was once I had all these models, up to that point I started thinking on maybe I should make a Eurorack model with this. And then I ported back everything to hardware, and what I'm doing now is backporting again. So I want to do like a clone of my own Eurorack module, but for VCV Rack. So that will simulate all the parts, like even the LCD screens and stuff like that. So yeah, it is very approachable, VCV Rack, because Eurorack is expensive.
I think it's funny that you started modeling hardware with software.
Yeah, that's what I mentioned, that I cannot decide if I like software or hardware the most, because I'm always like blurring the lines of I mean, it's difficult to know what is hardware and what is software in this sense, because I have software that simulates analog and hardware that simulates digital. Or
shifting gears a little bit, you have also made a language to help you with the signal processing pieces. Could you tell me about that?
Yes, I have the Vult language, which is a very simple language that I developed to gain kind of portability, because some years ago, when I was doing all these synthesizers using different microcontrollers, I would make some piece of code, for example, for a DSP. And when I had something done, then a new development board comes out and I want it, and then I develop something for it. And I started getting problems like moving my code. So I decided to make like this layer on top of C++. That will be a much simpler language, less things to worry about, and that I could later create different generators to target the different platforms that I wanted to do. So, for example, I will make with this Vult language an oscillator, and then I could, if I wanted to run it on a web browser, I can generate JavaScript and then use the web audio API to test the sound, or even develop it directly in the web browser. And once I'm satisfied with it, I can generate the C++ code that I want to run, for example, on a Teensy board, or probably in an Arduino if it's possible, without making changes. So I wanted to concentrate all my development into this language, and being able of moving it, but also adding features that I always use. For example, creation of lookup tables. And in other projects where I have done with lookup tables, I use like any external software to do the calculations and then write a file and then doing it into C++. But with the Vult language, I can just write a formula and say like, this formula is going to be a lookup table of this size. I'm going to use interpolation, etc. And when compiling the code, it does all the calculations, and I get the optimized code. And I also have features or more restrictions in the language. For example, when converting integers and floating point values, one error that I hit a lot before, it was in C++. When you write a number one, it can be an integer, it can be a double, it can be a floating point. I mean, double precision or single precision. And if you write the incorrect one, the C compiler will will assume which one it is, right? So it can be that you wanted to use single precision, but since you didn't write the F after the number, it thinks it's double precision, and then just your compiled code could be making double precision calculations and then convert it back to single precision. And I found that was actually consuming time. So in the language, I also put like very strict restrictions on the conversion of types. Like everything needs to be explicit. And yeah, a lot of small things like that I cover with the Vult compiler. And that's what I use for my development.
Are other people using the language, or is it just for you?
I mean, I'm developing just for me, and there are a few persons that use it, and a lot more trying to use it. But since I don't have very good documentation on it, maybe that's a key factor. But at least the persons that I know that use it, they like it a lot.
And would I have to already have solved all of my equations, and this is just putting in the forward methodology, or will it also help me figure out the equations, the differential equation solutions?
No, for the differential equations, so the Vult language is just for the final implementation.
Okay.
And for doing all the differential equations, as I mentioned before, I work in Wolfram research, and I work in the group that develops a Wolfram System Modeler, which is a tool for modeling systems. And that's the software I use where I do all my work with the electrical components. And it's a graphical interface, right? So I can recreate my whole circuit with that tool. And then I use Mathematica to extract the equations. And in Mathematica is where I do all the manipulation and all the testing and prototyping at the equation level, because it has a lot of tools for doing that.
That's mostly symbolic manipulation at that point, or is it already numeric?
No, it's completely symbolic.
Okay.
Because I want to get, I want to really use the symbolic capabilities to eliminate as much as possible of the calculations.
You say you don't have good documentation, but I'm looking at the Easy DSP with Vult page, and it walks through the whole thing. He starts with a filter and shows how to write a function that matches that filter, and then it's. I mean, obviously, it's not going to do the hard part for you of doing the math, but this starts with that a little bit and goes through it. So
yes, yeah. I mean, I don't have documentation for all the cool features for the new features that I have implemented.
Does it integrate with the VCV modular synthesizer? VCV Rack?
It integrates through a plugin. So in VCV Rack, there is a plugin that is called the VCV prototype, and that module allows you to write in a single file code and then test it. And I use that one a lot as well for my development, because so I actually contributed that part of the plugin, being able of running Vult code in real time. So when I'm developing, I open this module, and then I have my text file with my code, and I type it. And when you hit save, it immediately starts running in VCV Rack, and it is really, really useful that you can just test, prototype, and test the code.
Really cool. Look, I don't need any more hobbies, Leonardo. This is very awesome stuff.
I will send you some links later.
If someone hypothetically wanted to get started with this, with creating the models and maybe not having a PhD in this in this sort of thing, is there a way to get started?
Yes, I think that. I mean, the best. It totally depends on what you want to achieve, because you can do modules that are nice, that sound nice, that are useful, and that do not require all the kind of detail that I put behind. I just do it because I know how to do it, and And definitely the best way to start is for example with VCV Rack. And I actually have some tutorials. I recorded like a 3-hour tutorial on YouTube, on my YouTube channel, where I show the whole process that I follow. And so I show the modeling part and also the implementation. That will be one of the resources that you can use. But definitely, a person does not need to go into the modeling in order to do something interesting and that sounds nice. If you want to go into the modeling, probably it will worth revisiting all the theory behind electric circuits and simulation methods, etc.
I have a listener question from Emily. As someone who's always interested in modular synths, but put off by the price, do you have any advice for how to get started on a budget? Is this going to be VCV Rack?
Yes, I think that the best way of doing that will be using a hybrid setup. So you can install VCV Rack for free, and then you can get a module that converts that helps you bridge the modular side and also the real Eurorack and the virtual Eurorack. And there are different modules. For example, the expert sleepers modules, which they are basically a sound card with many channels, and that helps you combine virtual modules with your real modules. So if you have like on the virtual side, you can have 1,000 modules, then you have your bridge and a few Eurorack modules just for the sound design, or also, the real Eurorack has the advantage that you can touch the controls,
right?
And that helps you a lot when performing and when doing when experimenting. So the modules that you think that are good for Eurorack to have on the Eurorack side, you can pick those and use them there. So definitely, just going back, because a hybrid setup of something virtual and analog, something virtual, something real, and the bridge, it will be a good start point.
Are the VCV Rack modules expensive?
No. The software is open source. There are like almost 2,000 free modules. I have myself, I have probably 20 something modules free, and there are a few that are paid modules, and those tend to be cheap, probably less than $20.
So if I wanted to try modular synths for really cheap, I could do all virtual and
Yes.
then slowly build up into physical world as well.
Yes, and that will help you a lot to decide what you want in the real world.
I have one more question that I think is just going to be the end of the show, and that is, I hear you're coming out with something to do with drums, and I didn't tell Christopher that ahead of time.
Oh, yeah. So the last months I've been modeling drums, analog drums. And
they just go bap, 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 right?
Why are you like this?
Something like that.
Boom, bap, 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 pss.
Pss, pss. And these drum modules are kind of fascinating, that how the original designer of the circuits developed them. So if one thinks, how can I make some like a cymbal sound? Oh yeah, I just need a noise source, envelopes, etc., or a clap sound. That was super interesting for me.
Yeah,
because how one will make a clap sound, and while I was analyzing those modules, I found out like a lot of interesting things, that if you don't model something. If you don't model the behavior or the transition curve of this transistor, you don't get a good sound. So I'm developing drum models, and probably in the future I will I will make another hardware module containing those.
Wait a minute, go back. If you don't model the what part of the drum sound?
The transition, the non-linearity of the transistor.
Oh, okay.
Yeah, because drum sounds are weird.
It's super impulsive.
Synth sounds, you can get your head around because, okay, I've got a sine wave or a triangle wave, and then I do this and that. But drums are a very complex mix of noise and transients and also pure tones and resonances. Like for a bass drum is a very low pure tone combined with the slap and all that stuff. So I've always been kind of fascinated by the analog drum synthesizers because it's like, okay, they have to kind of purpose build a bunch of circuits. It's not just one synthesizer that you can kind of make anything with. It's like, oh, I have to have something over here to work to make a snare, but it doesn't really work for the kick drum, so I have to have some extra stuff for that. Is that right? They kind of have to be a little bit purpose built?
Yes. For example, the case that I mentioned before with the clap, you have some noise source, and then you have envelopes to do the triggers. But in order to when I was trying to model it, there is a part in which you see a VCA. Just it's basically a multiplication. And if you do a basic multiplication of the voltages, you don't get the sound. So it needs to be like this specific transistor-based VCA. That way you get the correct transient when changing, when modulating the amplitude. And only if you use this VCA, you will get something that sounds like the original.
Yeah.
Well, wouldn't it be simpler to model the original sound? I mean, model the hand clap instead of model the transistor electronics that models the hand clap?
How do you model a hand clap?
I mean, you can always record the hand, like people clapping, and use a sample. That's the simplest model, probably.
There are physical modeling synthesis, like where you there's piano models. I have one that's quite good, and it's totally fake, and they've gone through and figured out how pianos work and model it that way. But that's more of a simple thing. You have a hammer and then the pure tone from the string. I don't know how you model something as weird as just an impact with the skin.
Mm-hmm.
It's interesting.
So one interesting thing about the drums is that for example, the 808, the Roland 808 drum machine, the designers were trying to do something that sounded like drums. It ended up not sounding like a real drum kit, but the fact that sound was different and unique, it made it super influential in the 80s music.
That's probably like the most famous. When people think of analog drums, that's the synthesizer I think people gravitate to thinking about.
Yes.
I'm still boggled by you going through electronics because it seems like the physical model would be simpler, and the electronics people had to have done the physical model at some point.
Well, but he correct me if I'm wrong. You're following on from the analog drum synths of the past, so you're trying to recreate kind of that sound. You're not out there to make realistic drum sounds in an analog synthesizer.
Yes. So, what I'm actually interested in is into learning how these drums work, and in in my learning process, I end up recreating them, and then I can just publish them for other people to use.
Yeah, if you want to make realistic drum sounds, you sample them.
Yes.
I have a question from Tom. Are the virtual synths really a good try before you buy sort of representation, or are there important differences between hardware and software implementations?
Okay, so actually in this question I didn't understand very well if it's like in general or for my specific.
I think in general.
Yeah, in general. I mean, if I'm hoping that for your specific, you'll say, "Oh no, they're rock solid, right on." But in general, are there things people should look for that indicate the differences are likely, or is this just a matter of reading the reviews?
I actually I don't know how to answer this one because as we were talking before, almost it's like everything works. As long as you like the sound, everything works.
Yeah, that's the thing about synths is you can get into a battle about virtual versus real, and it's like, but if it sounds good, who cares? So, and I think that
the main difference will be just the interface. The fact that you can touch it is what makes it different.
And that's a pretty big deal.
And I mean, if we reroute the question to my own stuff, in my personal case, the stuff that I have for free, it wasn't intended as try before you buy. But what ended up happening is that a lot of the people that tries my stuff, they tell me, yeah, I really like the filters. That's what I decided to get the hardware.
Cool. And we've talked a lot about all of this, and you've mentioned your job, but and you've mentioned using the simulators that are part of your job to fuel your side gig, fuel Vult. How do you lead this double life? How do you have time to lead this double life?
Yeah, it's complicated. So in Vult, I usually work just 1 hour, 2 hours during the night and during the weekends. But one nice thing is that since I'm using the tool that I'm developing for Wolfram, I usually come up with things that, okay, maybe, or it will be something like, probably I found a bug because I'm using our own tools, or I found something that could be improved. And at the same time, I have published through Wolfram some of the work that I do with Vult. I publish a blog post about how I use the tools to do that. So I think that we have a kind of nice symbiotic relation in which that is my hobby helps me with the work that I do at Wolfram. Also, in the development of the compiler, there are things that I try in my Vult language, experiments that I do, and sometimes I say like, oh, I really like the way that I make this part of the code. Probably we could apply it to the product to do better code or something like that.
Leonardo, do you have any thoughts you'd like to leave us with?
Yes, I just remember in a phrase from a famous statistician that he say that all models are fake, but some models are useful. And that's kind of the mantra of my life. So.
Our guest has been Leonardo Laguna Ruiz, founder of Vult. Check out his site, vult-dsp.com. We have links to that in the show notes, as well as to his wonderful YouTube tutorials.
Thanks, Leonardo.
Thank you. It was my pleasure.
Thank you to Christopher for producing and co-hosting. Thank you to Leonardo again for suggesting he be on the show and in the subject saying he wasn't a robot. And of course, thank you for listening. You can always contact us at show@embedded.fm or at the contact link on Embedded FM. And now I have a quote to leave you with from E.O. Wilson, which I always think of him as the ant guy, because that was the first nonfiction book I read that I enjoyed. We are drowning in information while starving for wisdom. The world henceforth will be run by synthesizers. People able to put together the right information at the right time, think critically about it, and make important choices wisely.